can get the first slide up. It's the green thing, right? Okay, that's actually the second one. Okay, good. Sanjay asked me to start off talking a little bit about the history of innovation in microelectronics. I'm guessing he may have noticed that there was an oversight. There wasn't a talk like that this morning. So we'll stick in just a little bit on that right now. I'll actually take one step back before Jack Kilby's invention of the integrated circuit and remind you that the silicon transistor was also invented here in Texas by Gordon Teal and Mort Jones. In fact, Gordon was in the very enviable position at a big microelectronics conference of being able to do a live demonstration of the superiority of silicon transistors over the previous germanium version at this conference, where a lot of the preceding speakers had lamented the fact that silicon transistors seemed to be way off on the horizon somewhere, or maybe never. And so he had started off his talk by saying, I've got some right here in my pocket, and did the demo, and then shortly thereafter there was this famous little snippet taken by a Motorola engineer who was calling back to his headquarters with the quote, "They've got the silicon transistor down in Texas." And that was a phrase that has made its way into a number of books and articles on the history of this industry, and I think started us off in a very good track on microelectronics innovation here. Of course, Jack Kilby's invention has been mentioned many times, and I've got a picture here of the 2000 class of Nobel laureates that Jack was in. Of course, Jack was a very tall gentleman. You can see over to the right, hard to miss. If you look second to the left, you'll see another gentleman in that class, Alan McDermott, who was one of the members of TAMEST, and who unfortunately also is no longer with us. Okay, now we get to another innovation in Texas that's debated, just like the invention of the integrated circuit was. I guess from my simple physics perspective, the difference in what was done at TI by Michael Cochran and Gary Boone and what was done at Intel was that they made a microcomputer rather than a microprocessor first. I mean, a lot of overlapping work here, and I'm sure the lawyers probably had a field day with this one as well. But to me, the difference is probably just that you've got some memory along with the microprocessor, and that makes it a microcomputer. And so there were a couple of firsts in this area back in the early 70s. Okay, a little bit more recently than that, but still a long time ago, and continuing to this day, is the continuing innovation that Larry Hornbeck has done in taking microelectronics to being actually microelectromechanical devices. And he invented, of course, what we called the digital micromirror device, which is still the major engine behind display technology that's projection-type display today. And so I assume that probably the very projector that we're looking at these photos on has Larry's DMDs behind it, these little micromirrors that we can manipulate electrically. So he won an Emmy for that, along with the American Institute of Physics Prize on Industrial Applications of Physics a few years ago. Another very significant invention along this trail towards where modern electronics has taken us is the first programmable DSP that Harvey Cragon worked on in the late 70s, early 80s, and this really led us into an era where we can begin to see the kind of societal impact that most of us appreciate individually today. This whole gamut of devices, all the way from, of course, cell phones, which are very heavily impacted by digital signal processing, to all kinds of other sensors and actuator associated electronics that we have today that to communicate with the real world and process the fundamentally analog signals digitally is really what was enabled by that invention. I have one slide here that adds just a few bullets to some of the things that have been mentioned earlier by Sanjay and Bill and Rich in terms of the impact of this industry on the country. I'll just point out a couple that weren't mentioned before. One of them is that this industry has been called by the U.S. government the #1 source of U.S. productivity growth. So if you just look at GNP growth percentage and try to peel that onion back and where does the growth come from. The number one source has been said to be information technology for quite a few years now, and of course the microelectronics is the backbone behind that. Also, the fact that this industry invests a relatively large amount, approximately 17% of its revenue, back in R&D. And there are very few industries that can say that. Perhaps pharmaceuticals can, and there may be one or two others, but typical big industry that you're associated with at the hundreds of billions of dollars levels invests a very much smaller amount of their revenue back in R&D. Now let's get on to the opportunity. So the opportunity that Sanjay and I in particular, and several other people in this room, are very interested in right now is where we go beyond the incumbent technology. And by incumbent technology for microelectronics, I'm talking about complementary MOS or CMOS. So do we have a way to get to another era beyond that? Just like we've transitioned from the early bipolar transistors to PMOS and then NMOS and then finally this complementary MOS. And that's a horse we've ridden for a very long time, and we know it's probably good for roughly another 10 years or so, even though we're not scaling it quite as fast as we used to at the transistor level. Overall, dimensions are still shrinking at the same rate, and so the whole chip is shrinking as fast. But if you look at that transistor gate length that Sanjay showed on one of his slides, that piece of it, which is a very fundamental piece, is no longer shrinking at the historical rate. And it's making a lot of us think about what does come next. At least can we find something that we put on the same circuit in a hybrid form that can supplement the CMOS and give us more of the kind of boost that we're used to from scaling CMOS. So that was the subject of the most recent issue of the Proceedings of the IEEE, special issue on nanoelectronics research, and in particular focusing on the possibility of beyond CMOS information processing. Now, the big initiative that Sanjay and several others in the room here are associated with right now in the US to tackle this problem is called the Nanoelectronics Research Initiative. It's a consortium of industry companies, IBM, Global Foundries, Intel, Micron, and TI, that began this consortium back in 2005, and we've partnered with both NIST and NSF, as well as with state governments, and in some cases even municipal governments, to fund this program. Basically, the program sponsors 4 large centers at universities, headquartered at individual universities, although many others are involved in each one, around the country. They're in California, Indiana, New York, and the one here in Texas called the Southwest Academy of Nanoelectronics that Sanjay is the director of. So we put in money along with our government partners, along with the Texas Emerging Technology Fund and the UT system to try to help our wonderful colleagues in the universities come up with the ideas on what can we do to get beyond CMOS, or at least complement it. So that's the challenge. We're definitely not idea limited in this area. That's the good news. It's a very hard problem, but it's great to at least be able to say that we're not idea limited. We have some wonderful ideas. One of the ones Sanjay mentioned earlier, this bipolar pseudospin field effect transistor, which is based on an amazing thought that Alan McDonald at UT Austin has had, that we might be able to create the world's first room temperature superfluid if we can put 2 layers of graphene closely juxtaposed in such a way that we can make excitons where the hole is on one layer of the graphene and the electron is on the other layer, but together they form one exciton. And so these are predicted by Alan's theory to be actually the ground state of the system at temperatures above room temperature. And so if indeed this is the case, if we can prove this in the next few years, Sanjay and his team can harness this into a device that we can use to process information, it'll certainly be a wonderful thing. But that's not the only idea. There are several other interesting devices that we're working on in NRI at many of these universities. Some involve nanomagnet logic, another one involves manipulating wave functions as if they were optical waves using p-in junctions that can refract the wave functions, again, in graphene. So graphene is a very important material in a number of the devices we're looking at. The only thing that we're really worried about in terms of keeping the ball rolling on this is, will we have enough funding to do justice to these wonderful ideas? So two things that are maybe just a little bit negative recently, of course, is the America Competes bill. And this is kind of a glass half full thing. Got reduced from the original House request of $85 billion down to $45 billion by the Senate. So, it's better than it could be, but not quite as good as we had hoped. And then, of course, it's already been mentioned that we have, of course, a deficit in Texas, and we don't know exactly yet what the impact that's going to be. But if we can marshal the resources here, I think we've got some very exciting days ahead, and I'm certainly very excited about working with my colleagues in the universities here, especially in Texas, on trying to make some of these dreams come true. Thank you.